So we're going to start off our discussion of infrared with a little game of remember when. Remember when I showed you an absorption spectrum and I pointed out that there were just a few lines that weren't there on the spectrum, some particular wavelengths or frequencies or energies of light that had been absorbed by, in this case, hydrogen. And then we showed you the emission spectrum in which we heated up or passed electricity through hydrogen and it gave off some light, and then we split that light up into its constituent frequencies and we found that it only had just a few energies of light contributing to that color, and those energies corresponded perfectly to the energies that had been absorbed when we just shined light through hydrogen without doing anything special to it. And of course the way that we explained this ultimately was that the energies allowed to electrons were quantized. There are only certain allowed energies which we describe as energy levels, and an electron could be there, or it could be there, or it could be there, or there, or there, but it couldn't be here in terms of energy. And so what we were seeing in the absorption spectrum was energy being absorbed by the hydrogen atom in order to bump an electron from the first to the second energy level, or maybe there was one from the first to the third or the first to the fourth, and this is why we only saw specific energies or frequencies or wavelengths, however you want to put it, being absorbed. And then of course with the emission ones we had excited the electrons up into these higher energy levels, and as they were relaxing back down to the ground state they were giving out specific energies, and those energies had to correspond to the energies that were absorbed here, because an absorption would be from 1 to 2 and the equivalent emission would be from 2 to 1. So we saw atoms have spectra. We used those to define the whole atomic theory, the idea that the energies associated with electrons were quantized. Well, molecules have spectra as well. The electrons in molecules are as quantized as the electrons are in atoms. So remember when we saw this. We saw this when thinking about transition metal compounds. We saw this when thinking about diazo dyes, because both of those were coloured. And the way that we explained that was that these electrons, the highest energy electrons in each of these, were in one particular orbital, and we'll call that n equals 1, even though there's all kinds of lower energy orbitals here. And then the first unoccupied orbital was n equals 2. And there was an energy gap between the two, so that when you shined light upon either a transition metal compound or a diazo compound, when the right absorption came along, an electron would pop from n equals 1 up to n equals 2. And it just so happens that for transition metal compounds and diazo dyes, that photon that's being absorbed, right, is in the visible light range. So in other words, the energy difference that we were looking at for transition metals and diazo dyes for an electron to go from one level to another level, that energy between them was in visible light. Now, of course, for transition metal compounds, we were talking about those orbitals being d orbitals. And for diazo dyes, we were talking about them being pi and pi star orbitals with that extended delocalized pi system, you might remember. So you're very, very familiar with the idea of electronic spectra, in which an electron pops from one energy level to another because the energies allowed to electrons are quantized. Well, with infrared spectroscopy, it's exactly the same idea. We're looking at the quantization of certain allowed energies. But when we're looking at infrared spectra, we're not talking about the quantization of electron levels, we're talking about the energies associated with bond vibrations. So here's a pretty little animation that it took me a while to do. Here's two atoms, X and Y, and we're going to say that they're bonded. Now, of course, X and Y, the atoms, are moving around, but because they're attached by a bond, they can't just move wherever they want. It makes it look like the bond is vibrating. So here's a nice little bond vibration. Now, if I shine light energy onto that bond, absolutely nothing will happen unless I happen to shine a light energy of exactly the right photon to take this bond vibration from one energy level up to another energy level. Now notice that the bond absorbed just the right type of photon, so now it's vibrating with higher energy. And there wasn't an in-between bit, it was vibrating at the lower energy, and then the photon went in and it's vibrating at that higher frequency. Okay, only a particular energy of light can be absorbed here to make it go from that slower vibration to the faster vibration. So in the same way that we see that electrons are quantized, bond vibrations are quantized. Now the energy gap for electrons to move from one level to another is usually in the visible or the ultraviolet range of the electromagnetic spectrum. For bond vibrations, it doesn't take as much energy to make a bond vibrate more, as we saw, and indeed the energy or the frequency of the light that you have to absorb in order to make a bond vibrate more takes place in the infrared part of the spectrum. Now we can generate a nice little equation that I'm not going to use mathematically that's associated with the frequency of light that's absorbed by a particular bond. So that's the frequency there. I use nu instead of f for frequency. Pi, of course, you're familiar with. Raised to the power of half you're familiar with, but here's these two other funky little symbols, and I'm not going to worry about those in any way, shape or form other than to just say what they're related to in terms with which you're already familiar. So this K here is associated with the strength of the bond. Okay, now if the bond gets stronger, that means that the frequency required to make it vibrate more is going to go up, and that should make sense. If you've got a nice strong bond, if you think about bonds as being springs, for example, the thicker the spring, the stronger the spring, the more energy you have to put in to make it vibrate faster. And we see this when we look at the frequency, and I'm using that in quotes, absorbed in the infrared spectrum for certain bonds. If we think about a single bond versus a double bond, which of course is stronger than a single bond, versus a triple bond, which is stronger than a double, which is of course stronger than a single. And if we look at the vibration frequencies of those in centimeters to the -1, I'll explain that in a minute, you can see that it only takes a frequency or an energy or wave number per centimeter of 1000 to 1300 to make that single bond vibrate at the higher level. It takes 1650 to 1820 to make a double bond vibrate at that level, and then there is actually a carbon-oxygen triple bond in carbon monoxide, and you need 2146 in order to bump that to the next vibrational level. Okay, so the stronger the bond, the higher the frequency that is going to be used from the infrared, the higher the frequency that is going to be absorbed to make the bond vibrate from the slower to the faster level. Now this bottom thing here, this mu, is associated with the mass of the atoms on the two ends of the bonds. The actual expression, the formula, is a reduced mass, and I'm not going to worry about it, but effectively it's to do with the mass. So therefore you can see that if this gets big, well then the frequency would get smaller. So the lighter the atoms, the higher the frequency acquired to make them vibrate more. And we can see that if we just look at a few nice simple bonds to carbon, carbon to hydrogen, carbon to oxygen, carbon and chlorine. As we go down here, that mass is getting bigger, and if the mass is getting bigger, we would expect the frequency to get smaller. And indeed it does. Close to 3000 for a carbon hydrogen bond to make it vibrate faster, 1000 to 1300 for the carbon oxygen single bond, we've already seen that one, and then for carbon chlorine bond 6 to 800. Okay, so the big take home of this particular part of the movie is that bond vibrations are quantized. They have energy levels. bonds can only vibrate in a certain way until you put in just the right kind of energy to make it vibrate in a different way. That energy falls in the infrared part of the spectrum, and the energy needed increases as the bond strength goes up, therefore more energy, higher energy or frequency for a triple bond compared to a double bond compared to a single bond, and the frequency decreases as the mass increases. Thus the lighter bonds, the energies at the ends of the bonds that are lighter, need much higher energy than the big, old, heavy, chunky ones like chlorine.